Let's begin with a foundational concept. Muscle loss is not inevitable, but it is highly probable without targeted action. From a biological standpoint, the process is known as sarcopenia, the progressive loss of skeletal muscle mass and strength. This begins as early as the third decade of life. By the time we reach our 60s and 70s, if left unchecked, sarcopenia can reduce lean muscle mass by up to 30%. The implications aren't just cosmetic. Reduced muscle mass affects metabolism, immune resilience, insulin sensitivity, cognitive health, and risk of injury. But perhaps the most compelling part of this equation is that muscle loss is modifiable. It is not a passive decline. It is a dynamic process influenced by both internal and external input. The primary drivers of muscle degradation are age, disuse, and undernutrition. Let's take each one briefly. With aging, there is a decline in anabolic hormone production, testosterone, growth hormone, and insulin-like growth factor 1. There's also a decrease in the number and responsiveness of satellite cells, the muscle's resident stem cells, that are essential for repair and regeneration. Add to this an increased sensitivity to catabolic signals like myostatin and inflammatory cytokines, and the muscle becomes more vulnerable to breakdown. Disuse is another potent trigger. The body is remarkably efficient at conserving energy, and muscle tissue is metabolically expensive. So when you're inactive, whether from sedentary behavior, bed rest, or even just significantly reduced activity levels, there's a rapid downregulation of protein synthesis pathways. What's often underappreciated is how quickly this happens. Even 7 to 10 days of inactivity can lead to noticeable decreases in muscle fiber cross-sectional area, especially in the lower body. Then there's nutrition. Undernutrition isn't just about calorie intake. It's about micronutrient status, amino acid availability, and nutrient timing. Inadequate intake of high-quality protein or deficiency in key vitamins like vitamin D, B12, or even magnesium can impair the anabolic response to feeding and exercise. The muscle essentially becomes resistant to growth signals. This is a phenomenon often referred to as anabolic resistance, and it becomes more pronounced with age. But the plasticity of muscle tissue works in our favor. Because muscle is constantly remodeling, even small strategic inputs can yield significant outcomes. Resistance training, for instance, is a signal that tells the body you need this tissue. Pair that with sufficient protein and nutrients that support mitochondrial health and hormonal balance, and you're sending a multi-layered message to retain or even grow muscle. The nervous system also plays a key role here. Muscle strength isn't just about the size of the fibers, it's about how effectively the nervous system recruits them. Motor neuron firing patterns, reflex loops, and proprioceptive feedback all adapt to use and disuse. Targeted interventions, especially those that combine mechanical tension, eccentric loading, and nutrient timing, can recalibrate these systems, leading to stronger, more functional muscle. So yes, muscle loss accelerates with age, disuse, and undernutrition, but every single one of those drivers is modifiable. The key is understanding the levers and pulling them intentionally, consistently, and with enough intensity to outpace the decline. Vitamin D is commonly associated with bone health, calcium absorption, and immune function, but that's only scratching the surface of its biological impact. When we talk about vitamin D, we're not just talking about a vitamin in the traditional sense. We're talking about a corticosteroid hormone that operates throughout the body, including within muscle tissue, with far-reaching effects. Understanding how it functions at the cellular level gives us insight into why it plays such a powerful role in muscle growth, repair, and metabolic optimization. Once ingested or synthesized in the skin through sun exposure, vitamin D is converted by the liver into 25-hydroxyvitamin D, the form measured in blood tests. This is then converted in the kidneys and in some muscle cells themselves into its active form, 1,25-dihydroxyvitamin D. This active form binds to the vitamin D receptor, VDR, which is expressed in many tissues, including skeletal muscle, and that's where the cascade begins. When vitamin D binds to VDR in muscle cells, it initiates gene transcription. This means it turns on and off specific genes that regulate the synthesis of muscle proteins, mitochondrial enzymes, and inflammatory mediators. One of the key benefits here is enhanced protein synthesis. This is crucial for muscle hypertrophy and repair, particularly after training or injury. Without adequate vitamin D signaling, muscle cells respond more slowly to these stimuli and recovery is compromised. Vitamin D also plays a critical role in regulating calcium within the muscle cell. Calcium is not just for bones, it's a signaling molecule that initiates muscle contraction. When you lift a weight or engage in high-intensity exercise, calcium is released inside the muscle cell, triggering the actin-myosin cross-bridge cycling that produces force. If intracellular calcium signaling is impaired, so is contractile strength, and over time, this contributes to weakness and atrophy. Metabolically, vitamin D impacts insulin sensitivity and mitochondrial efficiency. Studies show that muscle cells with sufficient vitamin D signaling exhibit greater glucose uptake, increased ATP production, and reduced oxidative stress. This translates into more efficient energy use during workouts and better recovery post-exercise. And when mitochondria function more efficiently, you're not only generating more energy, you're also generating less inflammatory byproducts. That matters because chronic low-grade inflammation is one of the primary drivers of muscle catabolism. Additionally, vitamin D modulates the activity of myostatin, a protein that inhibits muscle growth. High levels of myostatin blunt hypertrophy. Vitamin D downregulates myostatin expression, thereby removing one of the brakes on muscle development. Simultaneously, it enhances IGF-1 signaling and activates the mTOR pathway, two of the most well-established anabolic mechanisms in human physiology. This isn't just theory. Clinical trials in populations ranging from older adults to elite athletes have shown that correcting vitamin D deficiency leads to measurable improvements in muscle strength, power, and recovery times. And these changes can happen relatively quickly, within 2 to 4 weeks of achieving optimal blood levels. But while it may seem simplistic to say that vitamin D supports muscle, the truth is that it acts more like a hormone, binding to nuclear receptors, regulating gene expression, modulating intracellular signaling, and enhancing the fundamental biological processes that build, repair, and energize skeletal muscle. One of the most compelling aspects of vitamin D's role in human physiology is the speed at which it can influence muscle tissue. We're not talking about months of slow, gradual change. We're talking about measurable effects on muscle protein synthesis and breakdown occurring within as little as 14 days once optimal vitamin D levels are reached. This is not only fascinating from a biological standpoint, it has powerful implications for performance, rehabilitation, aging, and overall health. To understand why this happens so quickly, we need to look at how vitamin D interfaces with muscle cells at the molecular level. Once converted into its active form, H12-dihydroxyvitamin D, it enters muscle cells and binds to the vitamin D receptor, VDR, a nuclear receptor that controls the transcription of genes involved in muscle maintenance. These genes regulate everything from the production of structural proteins to the enzymes that control inflammation and repair. What is especially noteworthy is that many of these changes are not dependent on long-term structural remodeling. Instead, they're part of a rapid shift in intracellular signaling. When optimal vitamin D levels are achieved, typically considered to be serum 25 hydroxyvitamin D concentrations in the range of 30 to 40 m/ml or higher. mTOR signaling, a master regulator of muscle protein synthesis, becomes more active, and this leads to an upregulation of anabolic processes, meaning the body becomes more efficient at taking amino acids from the diet and converting them into new muscle tissue. At the same time, vitamin D actively suppresses catabolic pathways. One of the primary mechanisms involves downregulating proteins like myostatin and members of the FOXO family, which are involved in the activation of ubiquitin ligases, enzymes that tag muscle proteins for degradation. With less of that signaling, muscle breakdown slows down. And again, this doesn't take months. Clinical studies in previously deficient individuals show statistically significant improvements in muscle strength, functional performance, and protein synthesis within just 2 weeks of correcting vitamin D levels. These effects are magnified when combined with resistance training or adequate protein intake. In fact, one of the reasons muscle growth may plateau even with training and nutrition dialed in, is a hidden deficiency in vitamin D. The body needs the hormonal signal that conditions are favorable for growth. Without it, you may be training hard and eating well, but the intracellular machinery remains muted. Once vitamin D sufficiency is achieved, that machinery activates. Amino acid transporters are expressed more efficiently, mitochondrial function improves, and satellite cell activity is enhanced. Vitamin D also enhances calcium handling within the muscle fiber. This is crucial for contraction efficiency and muscle tension, but it also plays a role in signaling cascades that influence growth. Better calcium kinetics means stronger, more efficient contractions and less fatigue, both of which indirectly support greater training volume and recovery, further enhancing the muscle building process. So when we talk about vitamin D's ability to enhance protein synthesis and reduce muscle degradation in as little as 14 days, we're really describing a coordinated shift in both anabolic and anti-catabolic signaling that flips the switch from breakdown to build mode. And it happens faster than most people realize, provided the right levels are in place. Let's get specific about the kind of muscle fiber most affected by vitamin D status. Type 2 fibers, also known as fast twitch fibers. These are the muscle fibers responsible for generating explosive power, strength, and speed. They're the ones recruited during sprinting, jumping, heavy lifting, and any high-intensity or high-force movement. Importantly, these fibers are also the most susceptible to atrophy with age and inactivity, making them a critical target for anyone concerned with performance or longevity. Emerging research shows that vitamin D supplementation has a direct, measurable effect on type 2 muscle fiber hypertrophy, particularly when paired with resistance training. This is a key point. We're not just looking at general improvements in muscle tone or endurance. We're looking at structural adaptations in the most metabolically and functionally significant fibers in the human body. And the mechanism is both hormonal and genetic. When vitamin D reaches its active form, 125-dihydroxyvitamin D, it binds to the vitamin D receptor, VDR, expressed within muscle tissue. Type 2 fibers have been shown to express these receptors more densely than type I fibers. What that means is these fast twitch fibers are more responsive to the genomic effects of vitamin D signaling. Once activated, the VDR initiates transcription of genes related to cell growth, repair, and protein synthesis, all the machinery needed to increase fiber size and contractile force. Now pair that with resistance training. During high-load mechanical tension, especially in eccentric contractions, muscle fibers undergo microtrauma. This damage isn't a problem, it's the stimulus for adaptation. But whether or not that stimulus results in hypertrophy depends on what's happening at the molecular level. Without sufficient vitamin D, the anabolic signaling pathways like mTOR and IGF-1 are suboptimal, and satellite cell recruitment is impaired. You get less adaptation for the same effort. But with optimal vitamin D status, you're amplifying the body's response to training. Satellite cells proliferate more effectively. Protein turnover is increased in favor of synthesis, and recovery is faster, which means you can train more frequently or at higher intensities. There are also neuromuscular benefits that affect type 2 fiber recruitment. Vitamin D supports the function of fast-twitch motor neurons, the nerve cells that fire these fibers during movement. Better neuromuscular efficiency means improved coordination, greater rate of force development, and a lower threshold for recruiting these high subperfusion. In studies involving older adults and athletes alike, vitamin D supplementation has been linked to significant increases in type 2 fiber cross-sectional area. And again, the time frame isn't months, it's often within 4 to 6 weeks, with early shifts in signaling occurring within the first 14 days. It's not just that you feel stronger, the muscle fibers themselves are remodeling, increasing in density and diameter, especially when the training stimulus is present to guide the adaptation. So the equation is clear. Mechanical load plus sufficient protein plus optimal vitamin D equals maximized fast-twitch muscle growth. This is one of the most efficient ways to preserve power, strength, and metabolic vitality across the lifespan. To understand how vitamin D supports muscle preservation and growth, we have to explore its dual role in modulating inflammation and activating anabolic signaling, particularly through a central cellular pathway known as mTOR, or mechanistic target of rapamycin. This pathway is essentially the cell's internal sensor and switch for growth. When nutrients, hormones, and mechanical tension are present in the right combinations, mTOR is activated, and the machinery for building new proteins, repairing tissue, and increasing cell size is switched on. What's fascinating is that vitamin D plays a regulatory role in both suppressing catabolic inflammatory signals and promoting anabolic growth pathways like mTOR. This makes it uniquely positioned to control the balance between muscle breakdown and muscle building. First, let's talk about inflammation. Chronic low-grade inflammation, often driven by factors like poor sleep, stress, aging, and under-recovery from training, elevates circulating cytokines, especially IL-6, TNF-alpha, and CRP. These inflammatory markers are catabolic by nature. They promote muscle protein degradation and impair the insulin signaling needed to drive amino acids into muscle tissue. When these molecules are elevated, even with adequate training and nutrition, the body enters a state of resistance. It's not able to fully capitalize on anabolic stimuli. Vitamin D helps regulate the immune system by reducing the expression of these pro-immunitory cytokines while increasing anti-immunitory ones like IL-10. This shift in the cytokine environment creates a more favorable internal state for muscle recovery and growth. It also prevents muscle tissue from entering a chronic breakdown mode, which is often subtle and goes unnoticed until strength or performance begins to decline. Now, let's bring mTOR into the picture. The activation of the mTOR pathway is one of the most important intracellular signals for muscle hypertrophy. When mTOR is triggered, the cell ramps up the translation of muscle proteins, essentially converting dietary amino acids into new contractile tissue. mTOR also stimulates the growth of mitochondria, enhances nutrient uptake, and increases energy production, all of which contribute to stronger, more fatigue-resistant muscles. Vitamin D has been shown to upregulate mTOR signaling by modulating insulin sensitivity and increasing the phosphorylation of key downstream targets like P70, S6K, and 4-EPP1, both of which are directly involved in initiating protein synthesis. At the same time, it downregulates the FOXO family of transcription factors, which are responsible for turning on genes related to muscle degradation, including the ubiquitin-proteasome pathway. The result is a more favorable anabolic environment. Inflammation is down, recovery is up, and the cell is primed to build. And because vitamin D acts at the level of gene transcription, these effects are not surface level. They go deep into the programming of how the muscle cell decides what to do with incoming nutrients and mechanical signals from training. So what's powerful about this mechanism is the speed and reversibility. In individuals who are deficient, restoring optimal vitamin D levels often leads to improvements in both inflammatory markers and mTOR activity within days to weeks. This isn't a supplement that merely supports health in the background. It's actively directing the cellular economy of growth versus breakdown, with direct implications for performance, recovery, and long-term muscle preservation. One of the most critical but often overlooked consequences of vitamin D deficiency is its effect on two foundational systems that govern muscle health: satellite cell function and neuromuscular communication. These systems don't just influence muscle growth, they determine whether muscle is maintained or progressively lost over time. When vitamin D levels fall below optimal thresholds, both satellite cell activity and neuromuscular signaling begin to degrade. This sets off a cascade of physiological events that accelerates muscle breakdown, reduces performance, and impairs recovery. Let's start with satellite cells. These are the resident stem cells of skeletal muscle. They remain in a quiescent or inactive state until activated by mechanical stress, injury, or molecular signals. Once activated, they proliferate, differentiate, and fuse to existing muscle fibers, either repairing damaged tissue or donating nuclei to support growth. This process is not optional, it is essential for both regeneration and hypertrophy. Without functional satellite cells, the muscle's ability to respond to training or recover from stress is fundamentally compromised. Vitamin D directly regulates satellite cell activity through the vitamin D receptor, VDR, which is expressed in these cells. When VDR signaling is impaired due to deficiency, satellite cells show reduced proliferation and a decreased ability to differentiate. In other words, fewer cells are available for repair, and the ones that are present are less capable of supporting muscle regeneration. Over time, this leads to a decline in muscle quality, fewer functional fibers, more fibrosis, and slower recovery from even minor strain. Now, pair this with what's happening at the neuromuscular junction, the interface where motor neurons communicate with muscle fibers to generate contraction. Efficient neuromuscular communication is crucial for activating high-threshold motor units, particularly those that recruit type 2 fast-twitch fibers. These are the fibers that produce strength and power, and they're also the most vulnerable to age loss. Vitamin D is involved in maintaining the health and function of motor neurons, as well as the structural integrity of the neuromuscular junction itself. It enhances neurotransmitter release, improves synaptic efficiency, and modulates the expression of proteins involved in calcium handling and action potential propagation. When vitamin D is deficient, this means weaker, slower contractions and a reduced ability to activate the full range of muscle fibers, especially the fast, powerful ones. Over time, the reduced activation leads to disuse atrophy. Muscle fibers that are not regularly recruited begin to shrink. Compound this with impaired satellite cell support and increased inflammation, and the result is a perfect storm for muscle degradation. And the body doesn't wait long to make these adjustments. Research shows that even short-term vitamin D deficiency can increase markers of muscle protein breakdown and reduce anabolic signaling within just a few weeks. What we're looking at isn't just a nutrient deficiency, it's a system-wide disruption. The muscle loses its ability to regenerate, the nervous system loses its ability to command, and together they set the stage for accelerated loss of strength, size, and function. And all of it begins with something as modifiable as maintaining optimal vitamin D level. When we talk about optimizing vitamin D for muscle health, one of the most important factors is not just supplementation, but precision, specifically precision guided by blood work. This is not a case where more is better, nor is it one where guessing will get you results. For vitamin D to activate the full range of its benefits, enhancing protein synthesis, improving neuromuscular function, reducing inflammation, and supporting satellite cell activity, you have to be within a specific physiological range. That range is 30 to 40 plus nanograms per milliliter of serum 25 hydroxyvitamin D. Why is this the target? Because 25 OOD is the circulating form of vitamin D that your body uses as a stable indicator of total status. It reflects both dietary intake and what you synthesize from sunlight. Research has consistently shown that muscular performance benefits, including increased strength, faster recovery, and reduced rates of muscle loss, start to emerge when blood levels rise above the 30 m/ml threshold. Below this point, many of vitamin D's critical pathways are either partially activated or not activated at all. At suboptimal levels, let's say 20 m/ml or lower, your body is essentially in triage mode. That means vitamin D is diverted toward the most critical functions like calcium regulation for heart and nerve function, and away from optional systems like muscle growth or neuromuscular remodeling. But when you're in that 30-40 ml zone, vitamin D can begin to fully engage its anabolic roles. This includes upregulating mTOR signaling, improving mitochondrial performance, enhancing fast-twitch fiber function, and supporting satellite cell proliferation, all things we've already discussed as fundamental to building and preserving muscle tissue. Now, here's where precision matters. Individual responses to supplementation can vary widely. One person might need 1,000 IU per day to reach 35 m/ml, while another might require 0 IU or more, depending on factors like body weight, sun exposure, skin tone, gut absorption, and baseline deficiency. That's why relying solely on general recommendations is insufficient if your goal is performance or muscle retention. You need a baseline blood test. Testing your 25 OHD levels is simple and widely available, and it gives you an actionable biomarker. From there, you can titrate your intake accordingly. For many individuals, a maintenance dose of 2,000 to 400 IU per day will keep levels in the target range, though higher doses may be necessary short-term to correct a deficiency. Importantly, periodic retesting every 3 to 6 months is essential to avoid drifting below the optimal window or overshooting into potentially harmful excess. Also, context matters. Vitamin D is fat soluble, which means it should always be taken with dietary fat to enhance absorption. Some formulations also include vitamin K2, which may help with calcium balance, although the direct impact on muscle is still under investigation. The point is this: without precision, you're flying blind. With it, you're giving your system one of the most powerful modulators of muscle physiology that can begin showing results in as little as 14 days. And all it takes is data, a simple blood test, to calibrate a molecule that governs strength, repair, and performance from the inside out. So, what does all of this mean when we zoom out? It means that vitamin D is not just a background nutrient. It is a central regulatory force in muscle biology. From enhancing type 2 fiber hypertrophy to activating satellite cells, improving neuromuscular signaling, reducing inflammatory damage, and switching on mTOR-driven protein synthesis, vitamin D operates across multiple systems simultaneously. And the most striking part, these effects can begin in as little as 14 days, provided levels are optimized through precise, individualized dosing. This is about more than preventing deficiency. It's about unlocking performance, accelerating recovery, and protecting muscle integrity over the long term. Whether you're training for strength, recovering from injury, or simply aiming to maintain physical function as you age, vitamin D is one of the lowest cost, highest leverage tools available, but only if you treat it with the scientific precision it deserves. Measure, adjust, optimize, and let biology do the rest.